Measured, analytical. We picture quantum computers operating in pristine isolation. But beneath the advanced equations, these systems are anchored by severe physical vulnerabilities. Western governments treat the pursuit of quantum supremacy as a race of intellect and algorithm design. We see this reflected in policy, like the UK's commitment of £2.5 billion entirely focused on research, innovation, and skills development. Yet, as these systems move from proof of concept to deployment, the actual pace of progress is dictated by physical supply chains, not by qubit coherence times. Simultaneously, Beijing approaches the exact same industry with a different strategy. They treat the critical raw materials required for this hardware as a geo-economic weapon. China currently controls over 70% of global mining and upwards of 90% of global refining for the specific minerals that quantum systems require to function. They leverage this monopoly to construct an indigenous hardware ecosystem, deliberately walled off from foreign markets. By doing so, the Chinese state isolates its own technological development from the exact supply disruptions it can trigger abroad. To locate exactly where Western computing ambitions are exposed, we need to forensically deconstruct the physical hardware of a quantum computer. Controlling the quantum era requires mastering these physical manufacturing choke points. The outermost layer of that hardware is the dilution refrigerator. This apparatus cools quantum processors to temperatures below 10 millikelvin, colder than deep space, so that superconducting qubits lose their electrical resistance. Constructing these refrigerators relies on a strict oligopoly. 3 specific companies, Blueforce, Oxford Instruments, and Janus Research, control the market. Blueforce is the dominant supplier, and their current production throughput is roughly 1 system per day. Meanwhile, quantum developers iterate on their hardware architecture every 12 to 18 months, creating an immediate physical bottleneck for any rapid deployment scale. But the hardware itself is useless without the specialized fuel it requires to operate, helium-3. Helium-3 does not exist in any commercially extractable quantity in nature. It is almost exclusively harvested as a byproduct of tritium decay, sourced directly from maintaining stockpiles of nuclear weapons. Because of its origins, there is no transparent commercial market and no reliable long-term contract structure for acquiring it. Consequently, if a government or corporation attempts to deploy tens of thousands of quantum units, they currently have no viable method for sourcing the required fuel. Without solving the cryogenic supply chain, massive expansion is a physical impossibility. Moving past the cooling apparatus, the vulnerability deepens at the microscopic level of photonic circuits and silicon chips. To generate, control, and detect individual photons, optical components require specific, ultra-pure doses of erbium and ytterbium. Alternatively, systems using spin qubits, which encode information in the spin of electrons, face a different material hurdle. Spin qubits require isotopically pure silicon-28. This means manufacturers must undergo an intensely expensive process to strip out silicon-29, whose magnetic properties destroy quantum coherence. This chart illustrates the base concentration risk for these elements. China controls 69% of all global rare earth reserves, but unearthing the material is the minor hurdle. As the graphic shifts from reserves to high-purity processing, we see Beijing controls over 90% of the refinement capacity required for quantum applications.
And Beijing exercises this leverage. They recently instituted export controls targeting the specific technologies used for rare earth extraction and smelting. This processing monopoly extends to specialized compounds like lithium niobate. Lithium niobate is a nonlinear optical material. It is used to manufacture the electro-optic modulators that allow systems to route individual photons through a circuit without losing data. Chinese suppliers currently dominate 60 to 70% of the global market for high-quality lithium niobate crystal boules. Conversely, no supplier in the United States has the manufacturing capacity to produce these large-diameter, high-purity wafers at scale. The original patents and intellectual property for processing these crystals were developed in America, yet the actual manufacturing pipeline operates in Asia. Direct, you can design the most efficient photonic circuit on Earth, but you cannot build it if your geopolitical rival gatekeeps the raw crystals. Looking directly at China's domestic ecosystem, we see how they address these exact hardware requirements. This is Hefei, the geographic center of Chinese quantum scaling.
From here, state-backed companies have deployed systems like the 72-qubit Origin Wukong and the 504-qubit Tianyan 504. For Origin Wukong, 80% of its hardware, chips, and operating systems were sourced completely from domestic suppliers. This self-reliance is the result of continuous state planning, stemming directly from foundational research investments initiated by the Chinese government in 2001. By centralizing capital in the Hefei cluster, the state built a vertically integrated pipeline that connects raw material processing directly to final fabrication facilities. Western startups navigate highly fragmented, vulnerable global supply chains. The Hefei model operates as a closed, localized loop. Chinese institutes have successfully localized the production of everything from the quantum chips themselves to mass-producing their own dilution refrigerators. They are systematically inoculating their hardware sector against the very supply chain disruptions they are capable of inflicting on foreign markets. This matrix illustrates the strategic gap. On the left are Western objectives, like the UK's goal of 1 trillion quantum operations by 2035. On the right are compounding physical bottlenecks blocking that path. Reaching utility-scale computing is an industrial, manufacturing, and resource challenge. If Beijing expands its export controls to specifically choke off quantum-grade materials, Western commercialization will stall out. Their previous restrictions on gallium and germanium exports demonstrate their willingness to utilize this exact tactic. To mitigate this, Western policy must rapidly pivot from pure R&D to supply chain resilience over the next 18 to 24 months. First, allied nations must establish state-financed processing facilities, utilizing joint price floors to make domestic material production viable against Chinese state-subsidized dumping. Second, immediate capital must flow into pilot programs for rare earth refinement and the domestic production of large-diameter lithium niobate crystals. Third, the industry requires dedicated 300mm wafer-scale quantum fabrication plants to aggregate demand and localize chip manufacturing. Theoretical breakthroughs win Nobel Prizes, but secure, resilient supply chains will dictate who actually controls the quantum era.